videos we're going to discuss the consequences of global climate change, global warming, whatever it may be, on food. And that means not only the food we eat, but also, of course, the agriculture that produces the food for us, and indeed the food that we get by hunting and fishing. So all of those things are of interest to us as consumers, and all of them may or may not be affected by climate change to the extent that climate change happens. And those are the things we want to talk about. But in talking about climate change, it seemed a good idea that we should start at the beginning and ask the questions about how do we know about what's happening in the climate, what sort of measurements do we make, how do we make them, how often do we make them, and what do we use, how do we use that information in order to determine what's likely to happen in the future. And then with an understanding of that, we can go further and we can talk about the actual consequences that may exist for our food. So in order to help us understand something of that sort, we have with us today Ross Reynolds, who is a Senior Teaching Fellow and MSc Programme Director in the Department of Meteorology at the University of Reading, has a lot of experience in this area, has written books about weather and climate. Indeed, I was an editor for one of the books he did some years ago, and he's going to answer questions that I'm going to pose as a sort of substitute member of the public, asking questions about how do we know and how do we understand and how do we put these things together. Okay, so what we're going to do, what we're looking for is how do we know, how do we know, how do we know it, how do we make the measurements, and then towards the end of our discussion today, we will try to summarise in order to come to some conclusion. What do we mean when we talk about climate change and global warming? So let's start at the beginning and ask some questions. Let's start with temperature.
Right.
And let me ask you the question about how do we measure temperature. I mean, it's obvious how people do it now with thermometers, but there was a day when we didn't have thermometers and we didn't even have people, and yet scientists and others refer to times past and temperature. So let's start with that. And can you help? How do we measure temperature?
Okay, well, in terms of present day techniques for measuring temperature, we have in fact records that go back, the so-called Central England series, back to the 17th century, in fact, when thermometers was rather different from today. But in terms of standardisation, which is critically important, we still have weather screens, so-called Stevenson screens, in which we measure temperature, air temperature. So thermometers are still mercury and glass thermometers. We measure maximum temperature, minimum temperature, for two things anyway, inside the screen. And those were developed...
Excuse me, the screen is one of these boxes?
Slatted,
Slatted.
white painted
Yes,
boxes,
yes.
slatted boxes.
Right.
Named after a relative of Robert Louis Stevenson, in fact. Right. And they were developed, of course, by the Victorians. They're exposed in certain ways, in open areas, that kind of thing. So temperature has been measured over 120, 130 years reliably in that kind of way. We don't change anything. We don't suddenly decide to get rid of all the screens and have electronic instruments, which of course are popular nowadays. So we know that the temperature measurements, which are really classical, old-fashioned in a way, they're reliable and they have not changed over 100 plus years over a large area, kind of globally exactly, but during the Victorian era and later Victorian, observations spread very widely. So temperatures, when we talk about, it's going to be 20 degrees today, they're talking about inside the weather screen, not on top of your head or anything, or exposed in the sunlight. So we measure what you might call shade temperature. We do not want the sun to shine directly on the bulb, because that's not telling what the air temperature is, in fact. And there are many other ways of measuring temperature, from satellite, estimating them. We'll come to that maybe a bit later on. So we have reliable temperature series for stations that have not been affected by buildings near them, and the Met Office want to know if anything's changed in the local area in terms of temperature.
What do you do if it has?
Well, they just keep an eye on the record. They don't knock the building down or stop the recordings. They just make a note that maybe the overnight minimum temperature might be affected by construction within, a viewing distance of the screen. They just note it basically, and they might flag that observation as one that's not so reliable in a time series, for example.
But somehow you have to build that into the aggregate amount of information that you
Yeah, well there are, so you mentioned global warming, so the the mean temperature of the Earth is a concern. What do you mean by that? There are about 2,000 land stations that are used to compose land stations, a surface mean temperature. So what we do in terms of the mean temperature, typically, so in the day, you'll measure the maximum temperature and the minimum temperature in a 24-hour period, okay, with two different thermometers, and you average those two, and that's the daily mean temperature. So for August, you've got 31 daily mean temperatures. You get a monthly mean by averaging those 31. Then you get an annual mean temperature and so on and so forth. So that's a well understood, internationally accepted way of defining what the mean temperature is. Mm-hmm. Excuse me. And you have an overnight mean temperature, a mean minimum temperature, mean maximum temperature. It's a whole load of statistics that are reliable.
This is a 24-hour measurement, is it?
Yes, it is. So you can have, what's called a thermograph, an instrument that gives you a time trace of temperature, but the kind of internationally accepted ones are the max temperature and the min temperature, just one value within a 24-hour period of each of those parameters, basically.
Another question I want to ask you, and these Stevenson screens, are these standardised in design?
Yes, they are. Yes.
Worldwide?
Yes.
Okay.
Yeah. And there are certain, there is a World Met Organisation, WMO, not the word WHO. It's a UN agency based in Geneva, and they set the rules internationally. So all UN members are members of WMO, and they tell you what you have to do in terms of required accuracy, required exposure. There's internationally agreed standards, which that's been that way for a long time, not just recently. So the Stevenson screen, it's just a standard elevation, for example, above the ground. So there's got a double floor, so you don't get heat from the ground affecting the thermometer.
But what about heat island effects? The fact that
certainly the stations that are accepted are not ones that are not known not to be affected by urban growth, and which can of course lead to warming.
So some of them have been taken out of service as
like for example, Kew, for example, or Heathrow would not be used because it's affected by urban heat islands. So that it's very careful to to define the stations that are not affected by bias in that kind of way. Yes. Also over the ocean, there are about 1,200 drifting buoys that measure air temperature, and 4,000 or so ships in a given month that measure temperature globally of the air over the sea.
In a similar sort of way?
They don't have Stevenson screens, so their exposures are different because they have to be, you can't have a Stevenson screen on a buoy. Right. So those are measured differently. That's true.
But they do the same maximum minimum temperature.
Yes, they
24 hours.
Yes, yeah, that's right.
So in that sense, they're comparable over the whole area.
Yes, that's right. And there are data sparse areas, of course, too.
Well, that's another question I was going to ask. So what do you do about the data sparse areas?
Well, you might, for example, for sea surface temperature, to jump ahead, satellites are sensing sea surface temperature in cloud-free areas. As the buoys are too, they're not only measuring the atmospheric parameters, but also measuring the sea surface and temperature going down in the sea too. As are ships, or some research vessels in particular. So what they do is they appreciate, for example, in maybe the South Atlantic Ocean, there aren't the observations, and they will weight the observations. So over Africa there are data sparse areas too, it's just that weather services don't do a very good job, basically. So they weight the observations in terms of their significance, and there are data sparse areas, you can't get around that particularly, full stop. I can't say more than that actually. But certainly the geographical spread is as good as it can be. The high latitudes are quite well covered nowadays, but there are simply these perennial regions that are data sparse, like some African countries, like the Saharan countries, are not very good necessarily at keeping their records up to date.
What do you do about mountains, for example?
You measure temperature in mountain stations, for example, and of course it's colder the further you go up in the air. But that's part of that. What happens is when you're measuring, say, a European mean temperature, what they do is map the anomalies. They have a long-term climate, say for Zermatt or somewhere, for that station, and they will look at the anomalies for that station rather than the regional average will be slightly not biased. It will be affected by mountain stations, but they will also be warming at some rate. It doesn't matter whether you're up in a mountain or in the Dead Sea or whatever. The warming is kind of a universal
I think you need to
factor.
explain the word anomaly in this context.
Okay, so for example, if you're looking at European temperatures, say for this month of June,
Yes.
so for the whole of Europe, from northern Norway down to Sicily or Malta or wherever, you have a long-term, say 30-year average temperature for June.
Yes.
Okay. So what you do then is you look for June 2014 and you plot the anomalies compared to that long-term 30-year mean to get some
Anomaly, you
idea.
mean the difference
I
between...
beg your pardon, the departure from the average,
Yes,
I beg your
okay,
pardon.
yes,
Yeah.
right, okay.
Yeah.
So that must be a very important base then, and that goes back how far? 30 years?
You mean how far back we can go climate-wise in terms of
Well,
defining how? Yeah, so we can go back to the 1880s, 1870s, if that's what you mean.
Well, you're measuring an anomaly over a long-term...
Well, yeah, it's up for the Met Office, or whoever the users are to define WMO. So there are standard periods, so to speak. So it might be 1961 to 1990 or that kind of thing.
And these same periods are used as bases for all of the stations around
Yes.
the world?
Yes, and then you might shift to a more recent decade, for example.
Yes. But they're relatively short periods in the term of...
Yeah,
30
well,
years.
that's why the Victorians, I think it was, had a notion, or the Edwardians, that 30 years would define a climate, so to speak.
Okay.
We're not going to stuck with that a bit.
No, but it's just to get a concept of how long
Yeah.
the period is against which you're measuring anomalies or departures
Yeah.
from these sorts of things.
Yes.
Okay, now you mentioned, obviously you talked about thermometers, and these you said are standard mercury and
Right.
glass thermometers,
Right.
but there's also satellite measurement of temperature.
Yeah. I should say the minimum temperature is alcohol in glass.
Yes.
So satellites, they are capable of measuring surface temperatures, but what they do is sense the kind of long wave radiation that the surface of the Earth emits into space.
Yes.
So the hotter a surface is, the stronger that radiation going out is. So a satellite looking down and it's measuring a flow of radiation in watts per square metre. Actually, then you convert that into a temperature. Okay.
But in some areas it will be measuring, say, the ground,
Right.
and in other areas it will be measuring the tops of the trees in a forest.
Yeah, that's true.
So it's not
Yeah.
entirely comparable everywhere.
Well, no, over the so it's got to be cloud free for one thing, as I
Yes.
mentioned. But so the sea surface is where it's most greatest utility.
Yes.
Over the Sahara Desert, for example, it's also of greater utility. So in vegetated areas, you're quite right. In a kind of little picture element, might have a bit of scrubland and a bit of might be a square kilometre. So, but people know how to interpret that and which ones are making sense in terms of the surface temperature, not the air temperature, but the very surface temperature, which is not what you measure in the screen.
And the block is a kilometre, that's a standard.
Well, it depends on the resolution of the satellite. Some are better than that, like 10 metres, but typically a weather satellite,
Yes.
polar orbit has like a picture element that's about 1 kilometre square, essentially.
Yes.
So the sea surface temperature is very important to measure the very surface of the sea. The land surface temperature is also interesting, but it's the sea surface we're interested in terms of warming.
So with a satellite, with satellites in
Yeah.
plural, you have the possibility of measuring everywhere,
Yes.
pretty much. How much is in fact measured? How close are the measuring spots? How often are the measurements recorded and
Right.
made?
Right. Well, there are hundreds of thousands of measurements, a huge
Yes.
number every day.
Yes.
So you have two essential orbits. You have a so-called polar orbiter, which is about 1,000 kilometres above the surface, roughly.
Yes.
Doesn't go literally over the poles, but it does high latitudes and then comes around the Earth, rotating underneath it.
Yes.
So you're going to get a stripe of
Yes.
observations. And it is sensing many thousands of sea surface temperature measurements as it does one orbit, basically. The other one is a geosynchronous orbit, where the satellites are way out in space and moving around with the Earth. They have poorer resolution because they're further out, for one thing. Typically like maybe 2.5 or 5 kilometre squares. And they just fixed on one region because they're moving around with the Earth. They're giving you a shot every 30 minutes of maybe sea surface temperature or cloud amount or whatever it might be. So those two, they can't see the poles because of their angle of view.
Right.
So they're kind of complementary systems. So there are many hundreds of thousands of observations that flow into weather data centres just constantly, basically.
Okay, so the geostationary ones focus on a particular place and get frequent observations.
Full disk of the Earth, that's right.
Right.
Yeah.
And they get frequent observations, and that's
the same area.
Yes, and it's up to the operator to decide how often to take the...
Well, yeah, I think normally there are lots of things that people don't know called cloud motion vectors.
Yeah.
So we want to know about winds in the upper atmosphere. Not quite to the point here, but if some clouds drift with the wind, just some clouds. So if you have a 30-minute snapshot, the clouds are tracers of the wind. So that very big weather processing centres like the European Centre in Reading, they have hundreds of thousands of these cloud drift winds that fill in a huge area where there's no other data, basically.
Yes,
so the satellites, now you look at temperature, they're looking doing other things too.
Yeah, okay. And the polar ones then come around intermittently, and presumably they have a mechanism for locking onto particular places as they go around, so they repeatedly do.
Yeah, so what they do is, the Earth's rotating underneath and the stripe is maybe some hundreds of kilometres wide, and then what they do is they scan, they have a spinning mirror, so as they fly north, there's a mirror that's spinning around, it's scanning a line, and it's organised in such a way that the next line just touches the one to the south, if you see what I mean. So there's a lot of detail, and that's constantly transmitted. So the University of Dundee in the UK is a reception centre, for example, for that, and lots of data then.
And so how often does that get repeated? How often does the thing come back over
Okay,
the same place?
for the same area, 3 or 4 times a day.
Oh, I see, okay.
Yeah,
so
quite
just give an
frequent.
idea of how often it's going.
Yeah.
So in fact you get very comprehensive coverage of the whole of the globe, and you're measuring ground temperature, or at least ground or tops of trees, or
whatever it might be. That's right.
And you're measuring sea temperature.
Yeah.
Now what about the air temperature?
Well, satellites. All right. So we have weather balloons, or radiosondes, another word for them. There are about 600 of those around the world. They ideally should be launched 4 times a day, 0, 6, 12 and 18 GMT. So it's simultaneous, no matter where you are. So some countries they're about 120 quid a go. So it's £500 a day roughly. So some countries can't afford to do that. So so in the UK there are maybe 8 or 9 stations around the UK releasing balloons 4 times a day. So they sense as they go up every 5 or 10 seconds. Temperature, relative humidity, pressure, wind direction, wind speed. That's a standard kind of thing. Temperature and humidity at 0 and 12, wind over all those hours. So they go up to about 20 or 30 kilometres over an hour, or so, then burst and give you data coming back down again. Okay. So those are very unevenly spread around the world. There's about 600 reporting.
With large gaps, presumably?
Yeah, over the oceans, for example, over Africa. So the African nations might release 1 a day if you're lucky. It depends on the nation.
Yes.
So there are gaps. So then satellites, so they're looking up from the ground, floating up and drifting with the wind, and they go back to 1960s, 1950s, some of them. So,
but is that a serious lack of information not to have the
vertical profile?
The vertical profile in.
Well, it is. Well, we've got that, but also satellites. The polar orbiters look down and give us vertical profiles looking down very frequently in cloud-free areas, mainly.
Yes.
So they're filling in big gaps over the last 3 or 4 decades. That's been happening. So. And there are other satellites, that not weather ones, they're kind of ocean viewing satellites, and they have repeat periods of like 10 days. So there's a whole load of satellites, and the weather ones are very frequent for weather reasons. The ocean ones, because they're monitoring climate change, might give a repeat of 10 days in the same area, because there's not so much pressure for forecasting data from them. So it varies a lot. There's a whole load of satellites, environmental ones up there.
Now, you also mentioned cloud-free areas.
Right.
Would you like to hazard a guess what proportion of the Earth's surface is covered by cloud typically?
Very seasonally. Think of the mean albedo, or the reflection coefficient of the Earth. It's a bit of a guess, but less than half. A lot of the tropics, in particular, are more cloud-free, as you might imagine.
Yes.
The extratropical regions, or the polar regions in the summer are quite cloudy, for example. But those sometimes the cloud can persist for quite a few weeks, for example. Generally speaking, cloud systems are mobile. So it's not as if you've got a real big problem with half of Canada for 6 months is cloudy. So they tend to be moving feasts to the clouds kind of thing. So it's not a big problem.
But you said less than half. That means, as it were, more than a quarter.
Yeah.
So it's a sizable amount of the Earth actually covered by cloud.
Yeah.
Because the pictures one sees of the Earth from a distance show a lot of cloud.
Yeah, certainly a lot of tropical oceans are cloud-free and tropical land areas are cloud-free.
Yes. Okay, so that we know all this now in a lot of detail back certainly for 30, 40 years,
right.
and we have temperature measurements back, as you
100
say,
plus years, reliable.
in some areas.
Yes. Yeah.
Now, people also talk about ancient temperatures.
Yes.
So can you give us some idea?
Some notion of how they do
well,
that.
how they do it and how reliable and comprehensive such measurements are compared with modern ones.
Yeah. Well, there are a number of ways of estimating the temperature from the past. A number relying on, well, for one thing, people have heard of tree rings.
Yes.
In dendrochronology. So they stretch back to about 2,000 years, typically, with an annual resolution.
Over how wide an area?
Well, they're sampled fairly widely on land, of course. They tend to choose trees that are near their limit of growth, because they're more sensitive to precipitation, not just temperature. One famous region is the White Mountains of California, and in terms of some kind of tree there that's near its limit to growth. So I'm not a big expert in tree ring stuff, but they certainly are selected fairly widely in a widespread way to sample not just California, nowhere else on Earth kind of thing. But they will give information that's obviously independent from other kind of things I mentioned, back to say 2,000 years with pinpoint resolution to the very year. So that's one way of estimating temperature fluctuations.
But they're limited in the number of sites you can sample.
Yes, that
and
is
obviously
true.
none of the oceans.
No, well, exactly.
Yeah.
Certainly, glacier cores, so Greenland, of course, is a continental glacier, and the Antarctic ice masses. Antarctic was 6 kilometres thick in places. So what you can do, and you probably know, is you can take a core that may be over 1 kilometre long, much more than that in some cases, and draw the core out. And when snow falls on these ice masses, air is trapped in that snow, and it doesn't vanish. There are air bubbles that go back way down a few kilometres, and those air bubbles contain a mixture of gases like carbon dioxide. So it's not a new technique at all, isn't it? Dendrochronology is not a new technique. It's been around more than half a century or more. So ice cores are taken from kind of fairly carefully selected areas in those ice masses, and we can reconstruct, well, looking at the changes of carbon dioxide for one thing, back to over 100,000 years.
This gives you the carbon dioxide concentration
in air bubbles back to, of course the timing gets fuzzier the further down, as you might well imagine, the further down you go in the ice, because it gets more and more compressed.
But how can you be sure that the gas is not diffusing out through?
Well, I'm not an expert, but they know that's the case. I know what you're saying, whether it's been tainted in some way.
Yes.
But all I know is that isn't the case apparently. I mean, I can't say more than that because I'm not an expert in it. But
well, I can see that if the ice is laid down in large layers, then it would need to diffuse a long way to make much difference.
Well, that's right. I mean, so anyway, the fact is that they can look at CO2 concentrations back, back far into the distance. They can also look at 2 isotopes of oxygen, 18 and 16, and the ratio of those two will give you some feel for the relative temperatures when the ice was, or the snow was laid down to, and also some indication of sea levels indirectly.
I think you're going to need to explain how you...
Well, certainly it's related to the evaporation of seawater, which is supplying the ice in the first place. And again, I'm not a big expert in this, but the ratio of... So O16 I think is stable, and O18 is unstable, so that the ratio of those two is dependent, when they leave, the oxygen, so to speak, is evaporated within the water vapour, then condensed and deposited, okay? Then it's preserved, the ratio is preserved as the snow falls.
Yes, I presume that the higher the temperature, the easier it will be for the O18 in the water to come off, because it's that much heavier.
That's right.
Yes.
That's right.
Okay, so you can use the ratio then in the subsequent...
It's got a relative temperature variations, and whether it's related to carbon dioxide changes, for example.
So you can determine the concentrate ratio of oxygen, 16 oxygen 18, in the ice, which originated in the snowpack, and therefore reflects the precipitation, and therefore reflects the evaporation, and hence gives you some measure of.
It's not a logical, physical, reasonable physical link. No.
Is that a precise thing or a general?
No, it's a general, relative temperature fluctuation. So they attempt, you see graphs with, an attempt to put some value on it, but it's just a relative fluctuation. When it was much warmer, when it was much colder, and whether it's related to CO2 fluctuations too. So,
and that of course really only gives you data from the polar regions, or from glaciers?
Yeah, no, so continental glaciers, so Antarctica and Greenland.
Yes.
So the other kind of cores that are taken are from the ocean sediments.
Yes.
And there's a very big international program to do it very widely in the oceans. It's constantly going on. So they take cores in the ocean sediments, and they go back over 1 million years. Again, the time is fuzzy, as you might imagine.
Yes.
Because the sedimentation rates are very small.
Yes.
But they use the same kind, so they have, foraminifera, they have sort of micro fossil shells in the cores for one thing, and they look at the ratio of calcium and another element I've forgotten now, I'm afraid, in the shells, which again is so that they choose microfauna that are known to be surface living ones now, and their composition is known to relate to sea surface temperature today. So they look at how it's changed in the past in terms of 016, 018 also, I think, but certainly in the skeletal remains, microfauna. You can look at relative changes of cooler or warmer periods, and because there's a kind of strong relationship today with those microfauna and sea surface temperatures, then you can maybe infer kind of reasonable estimate of what the temperature was. In fact, the present is the key to the past, so to speak. So there's a very big international program with the global oceans taking course. That's much more widespread than the continental ice sheets. The point is that the dendrochronology is independent of the ice cores, is independent of the seabed cores, and they're all saying the same things in terms of the phasing, the dendrochronology more recently, the phasing of the changes and the kind of maybe the magnitude of the changes. So these are independently assessed methods, and they're saying the same thing essentially all over the place with different kinds of results, basically.
But obviously there's a big spread in precision with these.
Yeah, that's true. That's true.
From a thermometer which is...
Well, absolutely, of course.
To these which are much more estimated.
Yeah, I think so. The sea surface temperature one's a bit more reliable because there's and I can't say more on that basis.
No, that's fine. Yeah. I think that will help many people.
And this work is long-lived, so it's been going for decades. Yes. Suddenly popped up.
No, but I think just as it's helped me to hear what you have to say, I'm sure other people who are equally mystified in how these things are done will now know a bit more. Now, can we turn to the next thing, which is sea level? Right. And I want to bring up a few points which I read recently in a paper, that I don't want to discuss the paper, but it points out that changes in global sea level are caused by a change in the ocean basin volume, controlled by geological forces.
Right.
Change in seawater density resulting from variations in ocean temperatures and salinity, and the addition or subtraction of water from ice. Right. So those are primary ones, and then you get the coastal effects, the rise and fall of the land, the supply of sediments, the weather and climate which produces local effects, and ocean waves. Yes. Now all that's a very complicated picture. So and yet we hear statements that the sea level is rising. Yeah. Well, you obviously don't go down to the seashore with a meter stick and measure it. Well, what do you do?
Before I came to Reading, I worked for something called the Permanent Service for Mean Sea Level. That's in Birkenhead, or still is, University of Liverpool.
You're clearly an expert.
No, I haven't, like a long time ago. So the old-fashioned way, or if I can put it that way, and the traditional way is to measure sea level using tide gauges, and they are in place. There are over 100 around the shores of the UK and Ireland, for example. They have stilling wells in which there is a float that responds to sea level change. Or stilling wells are designed to nullify the effect of the choppy sea surface, for example. So when I worked in this place, they have a tide gauge inspectorate, so the job of going around to make sure there were no kind of conger reels stuck in the orifice.
But what do you do? Go and look at these things?
No, these are remote reading.
Okay.
Yeah, and harbour masters look after them.
Yes.
Okay, so that's an old-fashioned way, but still.
So that tells you the height of the highest tide.
Well, just it's constant. It's a float, so it's going up and down all the time. So there's a tidal cycle every 12.5 hours. There's a tidal cycle, depending on where you are.
It records continuously.
Yeah.
So
Okay. You get a digital readout. So
And over time, you can see differences in these levels.
yes, that's one thing. As you say, you rightly mentioned that the problem with that is, if you look at tide gauges in the Gulf of Bothnia, northern Baltic
Between
region,
Sweden and Finland.
Yeah.
Sorry.
you will find that the tide gauges are coming out of the sea, so to speak, because there's isostatic. There's a massive ice, huge amount of ice on so-called Fennoscandia. During the last ice age, maybe 20,000 years ago, there's a huge massive ice there.
Yes.
That's all melted, and the weight being taken off that crustal region means that the Earth's crust is doing this. So Finland and northern Sweden are coming out away from the centre of
And
the Earth.
bringing the sea up with them?
No, the sea appears to be dropping. So if you look at tide gauge records in the Gulf of Bothnia,
Yes.
sea level's falling, or it appears to be falling, because the land
Because
is...
the land-
Yeah, so you mentioned one problem. So
Yes.
it's not all plain sailing. And also sedimentation can affect, which of course happens in harbours.
So
Can
the
affect-
seabed actually rises?
Well, it gets mucked up with muck,
Yeah.
or sediment, if I can call it that. So people are aware of those
Yes.
problems. So some of the first indications of increasing civil weight, were tide gauges where we know that the region's crustally stable
Yes.
and you don't have so much sedimentation. So those tide gauges are focused upon. And they've been going over 100 years, the records have been going over 100, and they're fairly widespread, but they're kind of...
When you say fairly widespread, that's not
Well,
very
sorry, there are
precise.
thousands around the Earth.
All around the
thousands,
Earth, not
yeah.
just in Europe and North
No,
America.
that's right. So, since, maybe, I don't know, so late Victorian or
Okay.
early the 20th century, they were
So it's
set up.
given us 100
Yeah,
years.
yeah.
Yes.
That's one basis, but they're, it can be a bit difficult to unravel.
Yeah.
Satellites are, of course, a much more modern way of sensing
Yeah.
the sea surface. So what they do is, and we'll come to the complications, they operated with satellites, know precisely where satellites are, to incredible, just a few millimetres, compared to the ellipsoid, the kind of shape of the Earth, or theoretical shape of the Earth. So satellites send down a pulse of radiation to the sea surface and measure the kind of travel time of it back to the satellite. So they know how far the satellite is from the centre of the Earth,
Yes.
right? They know how far the sea surface is, even if it's ruffled or whatever, from the satellite. Okay, so they can pinpoint to a few millimetres, believe it or not, where the surface of the sea is with respect to the centre of the Earth.
The beam they're sending down is only a few millimetres in diameter.
No, beam is like just radiation. So they can measure what they do is send a pulse and measure the travel time from the satellite down to the sea
Okay, but
surface
the
and back
pulse
up.
is a small pulse, small
It's an
cross-section.
instantaneous pulse kind of thing. It's just a pulse of radiation.
No, but it hits a small area of
Oh,
sea.
I'm sorry, I beg your pardon. It illuminates a region that is a few metres. I'm not sure. I should know, but I don't know. Tens of metres or something
Oh,
like
tens
that.
of metres, so
Yeah.
it's going to average
An area
across a
average.
number of waves.
That's right. Yeah,
Things
but I'm not exactly sure about that.
Yeah, because I was wondering how you deal with wave tops versus
Well,
wave
yeah. Well,
troughs.
what they do for one thing. Another thing the satellites do, so as an aside, is that they measure the choppiness of the sea surface, and that is a function of wind speed.
Yes.
So weather forecast models are getting huge amounts of data from satellites of inferred winds over to improve forecasts. That's a different thing. So what satellites do, this repeat period of 10 days, I mentioned before, these sort of ocean viewing satellites. So they have to average over a number of cycles to get rid of the influence of waves on this signal. Also, the sea slopes. In fact,
You need
it's
to
not level.
explain that.
Yeah.
That sounds a
So
bit
what
odd.
I mean is, it's like an Irish joke or something. Irish skiers, water skiers. When you have a cup of tea,
Yes.
right? If it's an undisturbed cup of tea, the tea is flat.
Yes.
If you stir it and you produce a current in the tea, it sort of does that.
Yes.
Yeah. So the sea has currents, the oceans have currents.
Yes.
It might be a metre a second or tens of centimetres a second, and in response to that, the sea is actually sloping.
Oh, and of course, and weather patterns also...
Well, yeah, that's right. So you have surges. On the classic
Yes.
thing is a tropical cyclone with a surge of many metres high.
Yeah.
So, for example, if you measure sea level at Dover, say, your tide gauge, and this is the average, and you go across to somewhere on the French coast and measure sea level, it's not the same, because there's a slope on the sea surface. If you average it all out, get rid of the waves, get rid of the surgy bits, the sea actually slopes from England to France.
Does that mean there's a net flow of water down?
Yeah, it does, why, because there are currents involved with it.
And that's one of the things...
It's related to the currents, basically.
Yes, that's it.
So the currents, vary seasonally, it's all very... Anyway, so the fact is that people who process sea level data from satellites are aware of all these things, not as if they're all daft and they've forgotten everything. So that if you very carefully, which they do, get rid of the complications, not any kind of cheating kind of way, then you will find that in the open ocean, sea levels increasing, and around the coastal regions is increasing, and that they use tide gauges to corroborate satellite information too in certain specific areas. Okay, so sea level is increasing. Okay, it's very spatially. Okay, so it's kind of a global average you see that you can have asked about before. Now, how can you do that? So in some regions it's increasing more than other regions, but it's a global increase and it's really quite significant actually. It's explicable through, as you mentioned, some contribution is from large icebergs falling off Greenland or Antarctica. Floating ice is no good, so the Arctic sea ice melting does not increase sea level, like ice cube in a drink kind of thing. So it's the continental stuff, yeah. But it's also the fact that the sea is warming. That's not everywhere, but in the great majority of the oceans are warming down to at least 75 metres. Mm-hmm. That's measured from buoys. So the ocean's getting fatter, put it that way. It's expanding a bit, so that's an important component. You mentioned salinity is changing a bit too, and that's related to precipitation and evaporation changes. But people are very sure that sea level is increasing in a measurable way. Okay. And that the major cause, I would say, ocean basins changing shape is a possibility, and that I don't know how that's mapped, I should say. It's
that must be much slower.
Well, it is. It's geological time scale, isn't it? It'd be strange if it happened kind of globally too. It seems to me, in my ignorance, kind of thing. But so the principal causes are the warming and supply, other things too, but supply from the large ice masses too.
How much? Well,
not the whole story.
A number of questions piling up. First of all, a trivial one. What's the difference in height between England and France?
Oh, good question. It's the order of centimetres. It's not 10 metres or something, but it's measurable. Yeah.
Now, in terms of melting ice, how much difference would it make in the extreme if all the ice went?
Oh, good question.
I mean,
many tens of metres.
Oh, is it that much?
Yeah. On the Antarctic in particular, there's a huge kind of big fat lens of ice.
Yes.
And it will be tens of metres.
Yes. Now, I seem to have read places that ice is getting thicker in some places.
Yeah, in the Antarctic. That's right. That's true. I mean, the Arctic obviously is well known, news-wise, to be shrinking, and the Northwest Passage opening up, that kind of thing. And that's very likely to be related to sea surface temperature changing, but also, just as an aside, when you have sea ice, it reflects a lot of sunshine back to space. So like snow, a brilliant blue sky with sun shining really strong on the snow. It's not melting because it's reflecting at 90%. And the sea ice does the same. But if the sea ice is then gone, so the albedo, the reflection of sea ice is maybe 70%. If it's gone, then the reflection of sea is about 10%.
Sea water.
Yeah, sea water. Sorry, yeah. So if you change the nature of the surface from sea ice to no sea ice more extensively, there's got a positive feedback.
But why is the Antarctic ice getting thicker?
Well, because of weather systems. I think it's in the Southern Ocean is very busy in terms of depressions, these frontal depressions that produce lots of snow and rain in Britain. They are certainly a very significant circulation feature in the South Atlantic. Those oceans are warming in places. There's more evaporation into these systems and potentially more precipitation. It's probably that. Probably that. So it's not inconsistent.
But it's
warming.
a complex picture.
Yes, it is. Yes, it is. Yeah.
Okay, well, that's very helpful. Now, the next thing I would like to ask you, well, let's come to glaciers and ice, since we've already been talking about that. Tell us about the sorts of measurements that are made. We see newspaper reports about how glaciers are receding down the mountainsides and so forth.
Yeah.
So is this a significant factor in adding to the total water?
Probably not, because there are many kind of, montane or valley glaciers, obviously, and they are monitored globally, locally from, glaciologists, but also from satellites, very high resolution satellite imagery. But the amount of, increased stream flow, of course, will have a contribution to make, but it's fairly trivial compared to the enormity of Greenland, calving off the edge of Greenland, or the Antarctic continent, not everywhere, as you say, around
So
the
that's
Antarctic.
more indicative of, if you like, natural processes than actually adding...
Well, possibly. It could be warming, but I think it's true to say that the kind of mass budgets, the snow that falls in the winter and melts in the summer of glaciers are quite complicated. And sometimes quite relatively local effects can play a big role, and not globally necessarily.
But the total amount of water in land glaciers total amount of ice is small compared
Yes,
to what
it is.
in
It
Greenland.
is. Yeah, that's right. They obviously make a contribution, but it's quite small.
Yeah. Okay, and so is there a lot of variation in ice melting in different parts of the world?
Good question. That I'm not sure about, to be honest with you. From Greenland's point of view, on the eastern side into the kind of Denmark Straits and that kind of area, I think is an important region of, from that area losing ice. And again, I'm not knowledgeable enough in terms of the Antarctic continent to know. I think the Ross Ice Shelf, I think, for example, is suffering. I think that's right. But again, I'm not an expert in that kind of thing. So I honestly do not know whether, the montane valley glaciers in the Alps are shrinking more rapidly than the Rockies. They're quite small in the Rockies, I should say, actually really quite small. Or in the Canadian Arctic, for example. But snow cover is also known to be changing too, and that's, you're going to come to that, but that's also sent from satellites, very efficient, very effectively. And that's also a great example of a positive feedback, because snow, as I said before, reflects lots of sunshine, maybe 90% when it's fresh. If it starts to melt, then you have a bare rock surface or lichen surface that's much darker and absorbs sunshine much more effectively, and can boost the melting of the snow. So I can't say much more than that about the sort of ice volumes. I know the amount of ice falling off, so to speak, of the continental glaciers has really accelerated over the last 20 to 30 years. It's really become, so Greenland, I seem to remember, sort of a 6-fold increase in the estimates of ice coming off of it in a recent 20-year period to a not very far ago 20-year period.
Since you mentioned Greenland, I can't help remembering that Greenland was called Greenland because at one time it was green.
Around the edges, I think.
Well, maybe around the edges, but now not even around the edges. So in the time of the Vikings and so forth, the temperature was obviously warmer there. So what sort of as it were, industrial variation would one expect in temperature? Because
certainly looking at sort of tree rings and pollen analysis we didn't talk about, but, like birch versus oak pollen if you do cores in sort of lake bottoms and stuff. So over the last 1,000 years or so, there's interannual variability with, the Earth's mean temperature varies a bit from year. You'd expect that, like, a few tenths of a degree, it's just natural variability. But in the last 1,000 years, the temperature has, the medieval warm period, so-called, kind of just after the era of the Vikings, was maybe a degree warmer than previously, something like that.
And that makes that much difference?
What does, sorry?
A degree.
Yeah. Oh yeah, absolutely.
I mean, because that's really an important consideration, because when
it doesn't sound like much.
No, but when one talks about the possibility of warming effects as a result of current activities, people talk about a degree or two, it doesn't sound very much, but what you're suggesting from history is that it matters a great deal.
Yeah, absolutely, because, if you have, a hot summer, memorably hot summer, it's about 2 degrees more than average. Or a really chilly winter is 2 or 3 degrees colder. It's not much at all. So this notion of this 2-degree target that IPCC is kind of promoting if we go above that. It's just a nice round number basically, but it is a significant number basically. I mean, probably the difference in temperature between the last ice age and global temperature and now is about 3 to 4 degrees globally.
Yes,
And much more intense in some regions, obviously. Yes. Much more conservative in the tropics.
Yes.
But that's the kind of, it really is not a really big difference.
So when one talks about the medieval warm period versus the mini ice age of the 17th, 18th century.
It's the order of a degree, or something like that anyway, it's 1.5 degrees or something like that.
Okay.
So not massive.
No, okay. Yeah. Because that's an important consideration because of the sorts of temperatures that people think are possibilities for the coming period, could represent considerable differences in weather and climate with quite small. I should add that the medieval warm period and the Little Ice Age were kind of regionally biased. They didn't happen in Bolivia necessarily. So I should say the difference might be a bit bigger than that because it's going to be a European phenomenon for one thing. So it's a more regional thing. So it could be bigger than a degree. It might be I'm guessing 3 or 4 degrees, but not a massive number. Okay, now you've brought another interesting thing. You say it's a regional thing. I mean, are you saying that it did not happen, as it were, in Bolivia? I think so. So far as I understand it, I mean, the Little Ice Age is going to be a European phenomenon, I think, it's true to say. Yes. It wasn't happening, say, in Boston across the Atlantic, as far as I know, anyway. So how does it happen that the Earth's climate gets, as it were, out of kilter so much as to have these warm regional effects? Well, even today, for example, if you look at a year when it was unusually, you had a very cold winter, for example, recently, not this last one, but before. If you map that, it's the size of Western Europe, say. If you get a very cold anomaly in Western Europe, it's usually mapped because of circulation, how it works, with a warm anomaly further east, like in Western Russia, because of the nature of the weather patterns. What I mean is those are regional anomalies that are quite big, and they're produced by not just the jet stream, people focus too much on the jet stream, but they are forced by weather circulation anomalies again that produce a cold winter. Not everywhere in the Northern Hemisphere it wouldn't happen that way, but maybe the size of Europe or half the size of North America. They had a really, really cold spell when we had this really stormy winter recently, the floods and everything like that in this region of Europe. That was related to really, really cold air over eastern North America. They had really warm air in western North America. So what I'm saying is we still see kind of regional, by a region, I mean continent size, or half a continent. But still, these are relatively short-term effects. Yeah, they are, but for them to persist, that's right. These, I don't know how long the medieval period went on for. It's over, much longer than that's right. It was over kind of the definitions over a few centuries, but it wasn't persistent. So it's much more stable than these. Yeah, that's right. And understanding that is something else, of course. I think. Is there understanding? I mean, I don't want to tax you, but I'm not sure, to be honest with you. I mean, it's I can't answer that question, I'm afraid. Okay. And the Little Ice Age wasn't always, freezing winters for 30 years or something. Yeah, these famous frost fairs on the Thames. Right. And one factor about that is, of course, the Thames was really blocked up and the tidal waters didn't go up into like they do nowadays, and they're quite warm, the North Sea waters relatively. So one aspect of the ice fairs in London was that the Thames was kind of choked up with cold water, basically. Well, and London Bridge, actually. That's right. Yeah. That's right. Okay, fine. Thank you. That's very helpful. Now let's go on to actually getting towards some understanding. A little time on greenhouse gases, if you wouldn't mind. Yeah. You mentioned carbon dioxide. Right. There are other greenhouse gases which are involved. Water vapour, for example. Yes. So carbon dioxide, is one that we all think of. Obviously, it's increasing and measured to be increasing. It's just reached a record level, 400 parts per million. And I'll mention how it's measured and where it's measured. Yes. Anyway, so carbon dioxide is one. Water vapour, carbon dioxide is well mixed in the Earth's atmosphere. It comes from certain, sites of pollution like the industrialised world. But you measure carbon dioxide at the South Pole, it's the same as it is in the middle of the Pacific Ocean, the same as it is in London. It really mixes. Yes, it is, completely well mixed. Yes. Same as methane, that's all very well mixed. Nitrous oxide. Water vapour is highly biased geographically. It
it gets mixed up, but water vapor condenses into rain and falls out. It's not like the dry gases, so to speak.
Yeah.
So carbon dioxide in the kind of pre-industrial era of maybe 1750 and before that was about 280 parts per million. It's just reached for the first time in about 800,000 years 400 parts per million.
Yes.
We know because of these ice cores, it's never reached that. So in Mauna Loa is one of that was the first site to measure CO2 a long way away from any sources of pollution. Started in 1958. So there are over 1,000 CO2 measuring stations around the world, some near industrial sites. So we have very reliable, chemically analysed, I don't know how they do it because I'm not a chemist, data, just daily or more, probably daily resolution data. There's a very strong seasonal cycle, so CO2 is at its highest concentration just before in the northern hemisphere, spring starts, all these, like now, all these trees are gobbling up CO2 like mad because they're growing.
So
it drops. Yeah, so it's a very strong annual cycle, but there's a hell of a trend. So we
burn all the fuel in the winter time to keep warm and release carbon dioxide, and then the trees pick it up.
So that's right, gobbling it up, that's right. No, that's right, exactly. So that's a well-founded increase. The point about the word greenhouse is that these are very trace gases. You have, nitrogen is 70% of the Earth's atmosphere, oxygen, so like 99% of the Earth's atmosphere is nitrogen and oxygen, and they're of no consequence in terms of heating the surface of the Earth or the atmosphere. What's of consequence is that, parts per million CO2, parts per billion, doesn't matter how much trace concentration. Water vapour can be 1 or 2 or 3% of the atmosphere if it's really steamy.
But it's actually quite a powerful...
Yes, it is. Absolutely. That's very powerful too. So that, if that's mixed up with, CO2 concentrations are well mixed, but locally water vapour can act. So on a clear, just an example. So what happens, they're called greenhouse gases because the Earth is losing heat to space all the time.
Yeah.
It's overcome by sunshine in the daytime, so the temperature goes up, not enough. But at night time, it's still radiating to space now, and it's swamped by solar radiation coming in. But a lot of the long-wave radiation going out is absorbed selectively by CO2, water vapour. And some of that absorption is re-radiated, if that makes sense. Some of it's back down, some of it's sideways, some of it's up. So some of the radiation gets out, it doesn't block it completely, but it acts as a blanket.
Yes.
So if we had no greenhouse gases, the Earth would be 30 degrees Celsius colder than it is. So we're here because of greenhouse effect.
People talk about the absence of greenhouse gases on Mars as being part of the problem, and an excess of them as Venus.
That's right, exactly. Well, that's right, it's a good example. Yeah. So, it's part of our... the natural world.
We're said to be in the golden.
Well, the enhanced greenhouse gas is what we're, effect is what we're doing basically. Yeah. So if you increase the concentration of those gases, you would physically expect the temperature to go up. Basically, it's not unreasonable physically, isn't it?
Yes. Well, there's a lot of argument about that, which I don't want to get into.
Yeah. But if people who are kind of sceptical, they need to explain where the CO2 is coming from.
That's right. That they're all manner of things. Yeah. Okay. Now let's move on then to the last bit. The last thing I want to talk about is how do you put all this information together in order to come up with some simple statements? Right. And then I think we might finish by guessing as to what some of the consequences might be if this is really going the way many people think it is.
I mean, certainly, the IPCC, there are many scientists working on it. They're not all sort of pulling the wool over people's eyes, I think. I know there are people out there ought to, be sceptical.
I don't think we ought to...
No, sure, okay. But so the fact is that, we have it's a significant global warming. What's the word significant mean? Over the last 1,000 years, we might have seen, warming or cooling over degrees Celsius that might be associated with like little ice age or, quite small changes. Over the last 70 years or 50 years, we've seen an increase globally, and it is not everywhere in the world, but the vast majority of the planet at the surface is warming, and in the troposphere, the layer of the air below the stratosphere above our heads, is warmed by about 0.9 of a degree Celsius over 50 or 60 years, something like that, or a bit longer than that. And that's a very rapid increase.
Back to the war, more or less.
Well, kind of, that's right, yeah. So you need to explain that. It can't be kind of a, it's got to be explicable in some way physically.
Yes.
So that, the majority of scientists believe that it is due to human society, something in the last 50 years of warming, and there are these sort of phrases in IPCC, are kind of virtually certain, i.e. 95% or more probability that it's due to human society. We've got, we have inventories of coal burn, oil burn, what's pumped into the atmosphere.
How do we take this information, the information that you've described about how one gets it and the sort of information, how does one get it and boil it down into prediction and statements like it's getting 1 degree warmer or 2 degrees warmer? What's getting 1 degree warmer though?
Okay, well the global surface of the Earth. See, it's a kind of fuzzy thing, I suppose, is true to say.
Well, you say the global surface.
It's a planetary average.
But of the surface of the air?
No, I beg your pardon. Okay.
It's
all right, no, fine. All right, so we mentioned before early on that we're talking about the temperature in a weather screen, I suppose. That's what we measure.
Yes.
So the surface doesn't mean the slap bang on the floor. It means in the weather screen.
So that's 3 or 4 feet off the ground.
It's 1.6 metres.
Whatever it is.
I can't remember exactly. 1.8 maybe.
Yeah. So that's what it's
referring to. Yeah, that's right. But there's also the sea surface is warming, and that's a different kettle of fish.
Sea surface down to how far?
Slap bang on the surface of the sea.
Slap bang on the sea.
Yeah, it's the skin temperature of the sea.
All right.
And that then controls evaporation.
You mean if you were to dip a thermometer just into the top of the water?
Yeah, and that's what satellites measure, the skin temperature basically.
Right.
So it is, and if you look at the statistics or the actual map of temperature increase from, let's say, 1990 to 2010 or something, compared to the previous 20 years, say, the map would be mainly positive anomalies, so to speak. I mentioned before, very small. Some regions have got a bit cooler for a reason to understand, but whatever it is, 90% of the Earth's surface is warm. By surface, I mean we're talking about weather screen. That's a standard way of looking at temperature. So we have a kind of, well, not clumsy exactly. You've got to quantify it somehow, and it's a global mean temperature. You have 1,000 stations, whatever it is. You average them all, and then you come up with one fat number.
So there's some complicated calculation that goes.
Well, basically, that's right. I think, as I say, with the sea, the snow cover changes are kind of percentage-wise, and Arctic sea ice map from satellites are kind of percentage changes that can be converted into changes of area in terms of square kilometres lost, that kind of thing.
I mean, I know. I don't want to get anything like taking sides argument. And I know there are arguments, but is there any debate about this calculation, or is that?
No, I don't think so. It's basically, there may be some, as I said before, some gaps in the data, like over Saharan Africa. There are some gaps.
Yeah.
So the people who calculate the average somehow take that into account if there's a gap. They're not statistically, so to speak, if I can put it that way.
Okay.
So it's not a complicated thing to do. It's just averaging, maybe 900 stations or 1,000 stations that are well selected, basically.
Okay. So look, can we come to the last bit, because we are, in the end, we're going to be talking eventually about food in subsequent discussions. So what do you see as the implications which are likely to affect agriculture? The things that I can think of obviously are temperature and sunshine and rain and wind perhaps, and in the sea temperature again, currents, fishing. What do you see as being the consequences?
I think certainly, not being a kind of an agricultural specialist, but certainly increases in the temperature, obviously kind of globally, kind of regionally. There's a lot of regional detail available in these predictions, not just a smudgy, just one big value, So the most reliable in terms of the predictions for the future, obviously, are temperature. One really important thing that's been happening is that, I have student projects at Reading, for example. We have 50 or 60 years of daily data that, fogs are not agricultural, fogs are much less common because it's getting warmer. But the overnight minimum frosts are much less common than they were, and that's kind of not that you have frosts in equatorial Africa, but in frost-prone regions of the world, the number of frosts are going down. There are more incidences of higher temperatures.
That's interesting
Yeah,
because
because the temperatures are shifting upwards, so to speak.
as far as I remember, some plants need frost in order to germinate.
Right, okay, that's interesting. That's one of the important factors, that's right.
Well, when we get round to talking biology,
that's right. I think certainly so, and you know, more commonly extreme temperatures, depending on how you find extreme, depending on where you live, but more extreme temperatures, what I mean by that is extreme higher temperatures. A bigger problem for prediction is precipitation. It's a much more variable quantity in the atmosphere. But seasonal changes in precipitation are kind of fairly certain that, you know, in the mid-latitudes, winters are getting a bit wetter, and summers are getting a bit drier, for example. That's part of the signal. But predicting precipitation shifts is done, but those are less reliable than predicting temperature, say for the 2040s or something, or 2030s.
That's an interesting consideration. If there's more rainfall in winter and less in summer, then clearly plants could get flooded in winter.
Well, that's right, and you might need irrigation for longer or something, whatever it might be.
But on the other hand, you might in the course of time be able to improve irrigation techniques. And
that's right.
Okay.
So, and not being involved in this business of carbon dioxide concentrations increasing, does that affect some crops more than others in terms of productivity?
When we talk biology,
so that's kind of another kind of aspect of it, basically. I think in terms of storminess, I mean, well, in terms of, you know, you're living in the Caribbean with sea surface temperatures increasing, that might mean you would get more frequent hurricanes and or more intense hurricanes. And of course, you could have, you know, sugarcane crop destroyed in Dominica or something. That in terms of agriculture there's a bit of regional thing, and typhoons affecting the Philippines, and so it's kind of a tropically biased problem.
What about fishing and ocean currents and things like that?
Well, I think, you know, as far as I understand it, the ocean, or the temperature of the ocean's changing. I say it's increasing, so whether that means fish populations will migrate, I don't know what they do exactly.
No, we'll have to talk to a fisherman.
And the currents, so far as I understand it, there are, you know, seasonal variations in current strength and location, and I don't know more than that to me, and I can't say more than that, I'm afraid, but certainly the temperature and the salinity, there's acidification, I beg your pardon, of the oceans happening too, but that has some role to play. I don't know. So there's a whole lot of aspects.
Well, it will have at some level in the chain, because some organisms will be unable to grow the way they could, and therefore there will be a shift of some sort, but I'd say that's a question for the talking about. Okay, I think that's been extremely helpful, and I'm very grateful that you have been able to give such a clear account.
I hope I've, you know, done a satisfactory job.
Well, to all the questions I've asked, I mean, there have been a number of them, and I think that with all that under our belts, we'll be in a good position now to think about agriculture. Thank you very much.